So I hope my screen is visible.
Yes, it's okay.
Okay.
You can start.
So my topic is asymptotic inference in a quantum time series model. That will be a quantum version of a stationary Gaussian sequence. So this is joint work with Aletta Skola from Leipzig University. So let me begin with this slide, which shows a 1986 paper of Rafail and Adar, so which demonstrates that my topic is not too far from their interests. The paper was written, must have been written in the early 80s, because it's published in 86. That's early 80s is the time when I was a postdoc in Moscow. And this event my postdoc several years, has defined my whole career. So thank you both of you, both authors. Almost 40 years ago, I was in St. Petersburg, and I also remember that time fondly. So let's begin with a classical Gaussian stationary sequence. So we begin with some known results and some known theory. So a stationary Gaussian sequence, which has the stationary Gaussian, zero expectation, and it has an autocovariance function, which is given by the Fourier coefficients of the spectral density. F is the spectral density on minus pi to pi. The function is non-negative. It's symmetric around zero, and we observe a series of length n of that stationary Gaussian sequence. Assume that the spectral density is in a regular parametric class, with governed by theta by a d-dimensional parameter. One of the fundamental papers in this area is the one of Davis, 1973, asymptotic inference in a stationary Gaussian time series. So I try to model the title here a little bit after that. So Davis established LAN, local asymptotic normality, and also showed that the maximum likelihood estimator is asymptotically efficient in a parametric model. That was also one of the first paper which applied local asymptotic normality to any model after the definition of Lecam. So there is the monograph of Japaridze, 1986, which presents an extensive theory about LAN and related questions in stationary Gaussian time series. So in detail, let's formalize that a little bit. We consider a statistical experiment given by n-dimensional Gaussian observations and with zero expectation and a covariance matrix gamma n depending on the spectral density f theta. Gamma n of f is the Toeplitz covariance matrix. So the elements of the matrix, the matrix is Toeplitz, and it depends only on the difference of the two indices. So assume we have dimension 1, theta is an interval, then assume the model is regular, then it fulfills the standard LAN conditions with localization rate n to the minus 1/2 and normalized Fisher information, which is here, where the derivative of the log spectral density appears. So now from that parametric theory, let's go to asymptotic equivalence theory. So we now assume a non-parametric model, but first let's look what happens in the parametric case when we look at it from another angle. Namely, now let's consider a white noise model with the same asymptotic Fisher information. So signal in white noise on the same interval, minus pi to pi. Let's assume we have a function f theta depending on the parameter, which is one-dimensional, and we have the logarithm of that function. So if that is the spectral density, The F is the spectral density. Our signal is the logarithm of the spectral density. We have small noise, n⁻⁻², and that can be shown to be asymptotically equivalent in the parametric case, which is a consequence of LAN, local asymptotic normality, and that suggests that the asymptotic equivalence might also be true for a larger non-parametric spectral density class. So that's the result which we have shown with Yura Golubov and Harrison Joe in 2010, asymptotic equivalence of spectral density estimation and Gaussian white noise. So that's, let's describe that. So theta is the intersection of a periodic Sobolev class with a set Fm where the logarithm of the absolute value is bounded, which means that the spectral density is bounded away from 0 and bounded from above. We consider experiments where, given by the n-dimensional normal with 0 mean, the Toeplitz covariance matrix depending on the spectral density. And then we can show the delta distance becomes deficiency distance between these two models tends to 0. So Fn is the white noise model, and En is the spectral density model or the Gaussian stationary sequence. So Fn is the model 1, the white noise with, but not parametric this time, but just the spectral density in this class, in this non-parametric class. There's an intermediate step which consists in showing that an exponential regression model is also asymptotically equivalent. That is, we have a model of independent random variables. Each of these is exponential with parameter 2f of tj, where tj is an equispaced grid on the interval 0 to pi, so on half of that interval. So that's the well-known exponential density. Well, the exponential approximation has been present in time series theory for some time, but we have shown the actual equivalence in the sense of Lecam. Now, we are going to consider a quantum version of that model. So let me introduce quantum states and measurement. That's inevitable for every talk on quantum statistics for a general statistical audience. So we start with the Hilbert space of wave functions. That could be d-dimensional complex space, or it could be the L2 on the real line, complex value functions on the real line. And we consider states on that Hilbert space. The state is a density operator on the Hilbert space with a property it's self-adjoint, it's positive, and it has trace 1 normalized. A measurement of a quantum state is given by an observable. So we generate random variables from that state by considering operators. It's a self-adjoint, so X, let X be a self-adjoint operator in the Hilbert space, which has a spectral decomposition with a spectral measure, projection valued spectral measure, or also called resolution of the identity. So M of B assigns a projection to every Borel set on the real line. This generates a random variable according to the following principle. X is in probability that X is in the Borel set is trace of the state times the projector given by M of B, by the spectral measure. So every observable generates a random variable, and we use the same letters for them. Also X here. So X can be discrete or continuous depending on the spectrum of the operator. So a fundamental fact here is if the two operators do not commute, they do not have, then the two random variables don't have a joint distribution. So that means if we want to observe something, we must select between observables. We cannot get all of them at once, or even two of them at once if they do not commute. So if they're not commuting matrices or commuting operators. So one has to choose between measurements and accept in a commuting family of states. If the family of states commutes, then one measurement is good for all the states, and that converts it into a classical statistical problem. So when we have a family of quantum states which all commute among themselves, then we are basically back in the classical case. It's a special case of a probability distribution. So now let's, so we discussed general Gaussian states. Now let's consider Gaussian quantum states. So we considered a classical Gaussian stationary time series. Each is centered normal, expectation 0, variance sigma squared, and they have correlations. Now what's the analog of one Gaussian? x1, n0, sigma squared. So the analog of one Gaussian is given as follows. We take the Hilbert space L2 on the real line, complex valued functions, and consider a centered Gaussian state. So we'll have expectation 0 defined as follows. There are two basic operators or observables Q and P, which act as follows. Q to every function f of x, it assigns x f of x, and then there is a constant here, and p of f assigns the derivative. So they are multiplied by minus I. They are densely defined, not for every function, but for a dense set in the L2. And they do not commute because the commutator QP minus PQ is not 0. They don't commute. It's 2I times the identity. That's Heisenberg's commutation relation. So they don't commute. They're not jointly observable, and they play a fundamental role here. A state rho is defined as to be centered Gaussian if every linear combination of these two with coefficients h1, h2, they are real, is a centered Gaussian random variable, 0 h sigma h, h prime sigma h. So they can be shown to exist, and sigma is a real 2 by 2 covariance matrix. So we use the symbol here, n2 0 sigma. That's very much an analogy to the classical Gaussian, but we are using now blackboard mode. Another type. I hope that's a little bit clear. This is the ordinary Gaussian, ordinary n. We have a blackboard mode n2, but this notation emphasizes the analogy. It has 0 expectation. It has a covariance sigma, covariance matrix sigma. So it would be 2 by 2 here in the simplest case. So let's again emphasize the linear combinations, that the fact that we can observe them and they are Gaussian does not mean that Q and P are jointly Gaussian. In fact, they don't have a joint distribution. We can observe all of these linear combinations or only one of these linear combinations. We have to make a decision which one to observe. So let's consider a subclass of these states. So we restrict the covariance matrix. In the 2 by 2 case, it just means the covariance matrix is diagonal, sigma A times I2, and the condition A greater or equal to 1 is necessary here. That's Heisenberg's uncertainty relation, a consequence of that. So these states can be written, these quantum Gaussians, in a kind of geometric series, 1 minus p, and then the sum p to the power k, pk. They are projectors. They are rank 1 projectors given by the Hermite orthonormal basis of L2. So phi k star, a one-dimensional projector. And the p, the parameter of this so-called geometric distribution, quasi-geometric distribution, but it involves projections. That depends on the a as a minus 1 over a plus 1. So if a equal to 1, then P is 0, and we obtain the state which is a one-dimensional projector, the projector P sub 0. That's called the vacuum state. Otherwise, the state is not one-dimensional. It's infinite dimensional for a greater than 0, and it's called a thermal state. So we note that this is a geometric series. We can check by the trace. The trace must be 1. It's a quantum state. So take the trace of a projection, one-dimensional is 1. We get the geometric series, and the trace is 1. It also follows, if we take the observable with this spectrum here, the spectrum is defined in terms of these projections multiplied by k. The spectrum is all the non-negative integers. Then we will have a random variable which is discrete and concentrated on the non-negative integers, and it will be a geometric distribution, which we can easily check. So probability y equal to k, take this trace, it's 1 minus p to the power k, which is the geometric probability. So we have a geometric distribution. We have a random variable which has a geometric distribution. It turns out this operator, this observable, can be written in terms of p and q as q squared p squared minus 2, a factor 1 over 4. It's called a number operator because it measures, in some sense, the number of particles. It's discrete, so there can be 0 and any number of particles. Okay, now let's come to the statistical problem of estimating the variance. We consider independent thermal states and the tensor product. So tensor product, it's something analogous to IID observations or independent observations. We have seen all these states have the same set of eigenvectors, so they all commute, and the problem becomes classical. We just can apply the number operator to each of them. That's a sufficient statistic. And we can take geometric random variables, and we get just a bunch of IID geometric random variables, y sub j. And then straightforwardly and asymptotically efficient estimator is take the mean and 2 times the mean plus 1. So this quantum statistical problem becomes trivial. Now we are going to introduce dependence in the states to get the time series. Before that, let me do a digression here to the quantum Gaussian shift model. So statisticians all know very well the Gaussian shift model. The model where you have to estimate the mean in the normal distribution. Oh, here what's the analog of that here? The quantum state, basic one, 2-dimensional. The mean is mu. This is unknown this time, and let A be fixed, analog of the variance. So this has the form, we take the centered state, and on both sides it's multiplied by a certain unitary matrix, which and these states do not commute. They cannot be reduced to a classical model. The problem is here, which observable are we going to use to estimate the mean? We want an asymptotically efficient estimator of the mean. So Q is normal with mean mu1 first component, the P with the second component normal, but we want to estimate both. We cannot observe both simultaneously. We can take a linear combination, but that's also not the solution. Then we just estimate a linear combination. What shall we do by estimating both components simultaneously? The solution is given by Holivo, 1978. There is a best unbiased and minimax estimator. It's of true quantum nature. It's not a linear combination. I cannot write this down here. And it is a minimax estimator. The minimax risk for squared loss of the 2-dimensional mean 2a plus 1. That's called the Holivo bound in quantum statistics, well known. in the meantime, we can compare it with the classical bound in a two-dimensional classical normal. If we want to estimate mu with Euclidean loss, that it's two times the variance, the Fisher information bound, or the inverse of that, or the minimax estimator is just the data, but here it's different, and that's the Holloway bound. So we made this digression to explain still the basic difficulty of quantum statistics and how it works in this simple case when we estimate the mean of a normal distribution. And that's all explained in the monograph by Holloway, which appeared when I was a postdoc in Moscow, 1982. I purchased that at the time, but didn't read it. Anyway, got interested in quantum statistics later. Now let's come to the quantum Gaussian time series. We are going to introduce correlations. We have n-mode Gaussian states. They will be analogs of the multivariate normal law. And we consider the n-fold to get the basic Hilbert space. It's the n-fold also. So it should be tensor product n. And we have a bunch of canonical observables. For each of the L2s, we have a Q and a P. So we have Q sub j and P sub j. And we have n of these pairs. And we consider a centered Gaussian state with covariance matrix. So dimension is 2n, covariance matrix is sigma. It's a 2n by 2n real covariance matrix. Defined as follows: take the write down the vector of these operators or observables. A linear combination of these observables is Gaussian with the corresponding corresponding variance defined in terms of the covariance matrix sigma. Not every covariance matrix is possible here. There is a condition due to quantumness. The state, now we define stationarity. The state is shift invariant, stationary. So if we can shift the observables and get the same distribution, that means here shift invariance in that scheme, and which implies the covariance matrix sigma is block triplets. It consists of 2 by 2 submatrices, and they have a triplet structure. So for an ordinary triplets matrix, you have the elements which are constant along the diagonals. Now there are 2 by 2 matrices. We have a further condition, gauge invariant states. Gauge invariant states are a subclass. So we rearrange the observables, and we get a permutation of the basic covariance matrix sigma check. And the gauge invariance means I cannot explain the physical meaning of this here. Let's proceed in a formal mathematical way that the quadratic form h prime sigma check h can be written as a complex quadratic form with a complex matrix A, and h tilde, which is composed of the 2 parts of h. So, which means equivalently, the covariance matrix sigma check has this property: a real part of A, imaginary part minus imaginary part in this quadrant, imaginary part lower quadrant. And all, so it's we have 4 blocks. Each of the blocks is n times n, and each of these blocks is triplets. Due to stationarity, the A is a complex triplets matrix. In the special case, we have a thermal state, which we already know. Sigma check is just A, because a complex number which is self-adjoint is real, so it's just a real number. In the general case, it's an n-dimensional matrix, which is complex. It must be greater than the unit matrix. And that's called the symbol of the state. So we write it sigma check of A. So now we have, we characterize the gauge invariant Gaussian state as depending on a covariance, as having the covariance matrix which depends on the symbol. So basically, the symbol takes the place of the covariance matrix. It's a kind of complex covariance matrix. It's also triplets and positive. So once we have that, we can define a quantum spectral density. So now we have the statistical experiment. The symbol matrix is in a set of complex matrices. Because they are triplets, they can be defined in terms of a spectral density. Let's call this A omega on the same interval minus pi to pi. So a complex triplets matrix also can be represented by a spectral density, but it's a bit different now. The function is real, the A omega is real, but it's not symmetric. So the classical spectral density is symmetric around 0, but that's not the case for the quantum spectral density. We call this the quantum spectral density, and the coefficients, the Fourier coefficients of that, they have the property Aj is complex conjugate of A minus. These are complex analogs of the autocovariance matrices. So we have a quantum spectral density, and we have quantum correlations, which are complex. So our asymptotic setup is we write An for the symbol matrix as a function of the quantum spectral density, and we have a sequence of statistical experiments where, defined by the spectral density, for each n we have the corresponding symbol, the corresponding triplets matrix, and then we have the n-dimensional Gaussian state, or 2 n-dimensional, and the spectral density varies in a set. So how much time do I have? I have to probably abbreviate a little bit.
You have 7 minutes.
Oh, good. Okay. So now I will discuss a little bit the motivation. How did this model came about? How basically I found this model? It's in the literature. So we have this quantum statistical model. Note that if this quantum spectral density is constant, we obtain independent thermal states. So that's in analogy to the classical Gaussian stationary time series. If the spectral density is constant, we get IID observations, IID Gaussians. So in general, if the spectral density is not constant, this model is non-commutative. These states do not commute, though it's a true quantum model. And we are faced with the same problems. We want to estimate the spectral density, say we don't know which observables to take. Consider the paper where I got this model from, Mossonnier 2009, Journal Mathematical Physics. He considered the binary case. There are 2 spectral densities, and we try to discriminate between 2 states. That's a discrimination problem, which can be solved in the classical case by the Chernoff bound. And there's also a quantum Chernoff bound, which has been found in 2006. So consider the error of discrimination between 2 quantum states. This can be written as follows. P hat is a projection. I minus P hat is also a projection. That's an observable taking value 0 or 1. So it's like a test, a random variable which gives us a test, takes values 0 and 1. This is the total error probability. And then we have an error exponent that's a logarithm. Take the logarithm, there's exponential decrease, but we have to take a logarithm. Then we get the error exponent divided by n. So the usual framework of large deviations. And the best logarithmic error probability is a certain expression, a certain functional of the 2 spectral densities. This Mossonnier found by the quantum Chernoff bound, which turns out to be the same as in a very classical model, in a geometric regression model. So let's consider a classical Chernoff bound between two classical probability distributions as follows. Let A omega be a function, and we take a uniformly spaced design on minus pi to pi. Consider the product measure of geometric distributions with parameter p, which in turn depends on a, and the a is the value of the function at the design point. So we have design points, and it's like a regression model. We have design points that are uniformly spaced on the interval minus pi to pi. At each design point, we observe a random variable which has this geometric distribution governed by the function. So this whole model, the parameter is the function, or the values of the function at these design points. So we call this the geometric regression model. It turns out the classical Chernoff bound in this geometric regression model is the same as which has been found in the quantum time series for two Gaussian states by this author, Moissonnier, and which gave us the conjecture that they might be asymptotically equivalent in the sense of LeCam, that the quantum time series reduces to the geometric regression model asymptotically in the sense of LeCam equivalence. Why? Because what Moissonnier showed, well, he didn't notice that geometric connection here, but that he essentially showed that for this large deviation problem, the discrimination problem becomes asymptotically classical. It's the same as between two geometric regression functions. So, which gave us this idea, the conjecture, the quantum time series and the geometric regression model are asymptotically equivalent in the sense of LeCam. We need the quantum extension of LeCam's deficiency distance. Well, that has been done. That's known in the literature. This is by Guta, Kahn, and Jenshova. Has been used. So we use quantum extensions of Markov kernels. I will skip this a little bit here. It's very much analogous to classical LeCam, to the classical LeCam definitions. We have the lowercase delta, which is the deficiency of one experiment with respect to another, E1, deficiency of E1 with respect to E2. And then if the two-sided, the maximum of the two is the LeCam's delta distance, which uses quantum generalizations of Markov kernels.
Okay, you have 1 minute.
Okay, I will accelerate. Quantum asymptotic equivalence. So we write if the deficiency of one sequence with respect to another tends to 0, then the first sequence is asymptotically more informative. If they're both asymptotically more informative and less informative, they're asymptotically equivalent. Then the delta distance tends to 0. And now we come to the main theorems. We have a set of quantum spectral densities, and we consider experiments, the quantum Gaussian time series, and the geometric regression model. Our parameter space is a periodic Sobolev class and intersected with a class where the density is bounded away from 1. First theorem, in this non-parametric case, the quantum time series is asymptotically less informative than the geometric regression model. Okay, geometric regression model is more informative. We are trying to sandwich the quantum model into two geometric regression models. The other case, the bound from below, the informativity bound from below, is in a parametric case. So we have M dependence, there are only 2M plus 1. Quantum correlations are non-zero, the others are 0, which means we have M dependence. And in this case, we can show the geometric regression model is less informative than the quantum time series. That means in the latter case, we have an upper and a lower bound. That's the corollary in the case of this M dependence, which is a parametric model. The two are asymptotically equivalent. The quantum time series and the geometric regression model are asymptotically equivalent. I could speak about why is it the geometric law. I guess I'm over the time.
Yes.
Yeah, okay, that's all. Thank you.
Thank you very much. We would like, I want to thank all speakers from this session again. And we arrive at the last part of our conference. And now the chairman is Yuri Golubev. I